All right, so we are moving on to section 8.2, which is all about polar coordinates, which is moving our regular complex numbers into polar form and vice versa. This is something you're going to do a lot for those of you who are moving on to calculus. So I wanted to introduce it here so that when you see it later, it maybe won't be so offensive. Okay, so just a quick little review on what complex numbers actually are, right? So remember what we introduce in college algebra is the idea of an imaginary, right? An imaginary number. And an imaginary number is any number that can be written with an I. Okay, hold on. Let me see if I can get this to focus. Looks like not very focused. Okay, that's a little bit better. All right. So any number that can be written as BI, where B is a real number. Okay, so we talked about using I numbers, right? Our imaginary unit. Remember, I is the same thing as the square root of -1, right? We created I back when we were doing the quadratic formula. So if we ended up with a square root that had a negative number under it, we could, continue to simplify, right? So that's what an imaginary number is, but we're talking about complex numbers. So when you see complex numbers, this is any number that can be written as A plus BI, okay, where A and B are real numbers, okay? So imaginary is just one individual term that has an I. So I, negative I, 2/3 I square root of 2. Okay, those are all imaginary numbers. Complex numbers is when we have a real term added or subtracted with an imaginary number term, right? So here's some examples of some complex numbers. If we have 2 minus 4i, 3 minus 6i, 8 plus 3i, these are all complex numbers. And if I asked you to put them in order, right, from smallest to largest, we would kind of run into an issue, right? Because how would you order these? You look at them, and we could look at just their real number part and say, well, they're already in order because 2 comes first and then 3 and then 8. Or do we look at the imaginary part, right? -4i, -6i, -3i, do we order them by that? So it's kind of this weird thing where we can't really put them in order, right? So we have a fact. They're actually not linearly, I can't say it, linearly ordered, okay? Complex numbers are not linear, I can't say it, linearly ordered. Struggling with my mouth today. Okay, they're not linearly ordered. So what we're going to do is we're going to try to just visualize what this complex number would look like on a rectangular coordinate system. Now, a rectangular coordinate system is just our typical graph, right? But what we're looking at is basically a complex plane, okay? So what I want to do is I want to consider my x-axis my real numbers, okay? Real numbers on my horizontal axis, right? And then my y-axis, I'm going to use that one to represent my imaginary numbers, okay? So if I wanted to express or visualize 2 plus 3i, this would be my real number part, right? So it would kind of be like the 2 is my x and the 3i, right? That's my imaginary part. That would be my y. So I would go on my x-axis or my real number axis, I would go over 2. And then on my imaginary axis, I would go up 3. 1, 2, 3. And there's that point. Okay. So what we're going to do is we're going to represent this as a vector. Okay. So a vector represents that complex number. Okay. So this is the idea, is that we can represent it as a vector, because a vector we can visually see. We can think about adding and subtracting these and kind of where these vectors lie. We can also relate these vectors to trig functions here in a little bit by thinking about how that vector can create a reference triangle. Okay, so moving forward, what we're saying here is that each complex number, a plus bi, determines a unique position vector. Okay, with an initial point at 0, 0. Notice it's starting here at 0, 0. And then its ending, its terminal point is AB, which is the numbers from our complex number, right? Okay, so that's great. That's easy enough. We should all be able to go over and up or backwards and down. You know, we know how to plot points and just draw a vector through them. So let's look at how that might change a little bit when we get into adding or summing two complex numbers. Okay, so what I'm going to do is I'm going to use two different colors for each number. So here's my first number, right, that I'm going to add to the second number. So for my first number, I'm going to start at 0, 0. And again, this is my real numbers, right? And then my vertical axis is my imaginary numbers. So for my first number, this tells me that my x is going to be 2, right? And my y is going to be 1. So if there's no number written in front of the y, it's an implied 1, right? So I'm going to go forwards 2, right? And then up 1. So that's my first vector. So I'm going to go ahead and draw it with my little arrow. There's my first vector. And I want to add to that my second number. Now, because I'm adding on to this vector, I'm not going to start this second number back at 0, 0, because I'm adding it to this vector. So I'm going to start at the end of this vector, okay? And this one has an x value or a real number value of 3 and an imaginary number or a y value of 4. So from the end of this vector where this one ended, I'm now going to go forwards 3. So 1, 2, 3, right? And then up 4. 1, 2, 3, 4. So that's where this vector ends. Okay. So wherever it ends, that's the vector that is created by this addition. In other words, my answer from adding my first vector to my second vector should be this blue vector. Okay, so we're just going to double check it. We've added complex numbers before, right? We know to add the real number part and add the imaginary part. So if I add 2 and 3, that gives me 5, right? If I add 1i and 4i, that gives me 5i. So I can check to make sure I ended up at the right place. If I look at this blue vector that I'm considering to be my answer, notice it's at 1, 2, 3, 4, 5 on the real number axis, which is the real number we got. And its y value, 1, 2, 3, 4, is up here at 5 on my imaginary axis. Okay. So we can just add like terms to get the new complex number, but I like this idea of being able to visualize how we're getting that new vector. It's taking our first vector, adding on our second vector, and ending up with a totally new vector that starts at that initial point 0, 0. Okay, let's look at another one. Same idea, and then we'll kind of generalize it and tie it to our trig functions. Okay. All right, so on this one, we have 6 minus 2i, and we're adding negative 4 minus 3i to that. So this is my first number. So my real number part, or my x, is going to be the 6. My imaginary part of this number is going to be the negative 2i, right? So to graph this first one, my x is going to be 6. 1, 2, 3, 4, 5, 6. And then because my y is negative, that means I'm going to go down 2. So this is what my first vector looks like. Okay, sorry, I had to turn my paper to be able to draw it. And then I'm going to add on this second number. Okay, notice my second number values are negative, right? My x here is going to be a -4, and my y is going to be a -3. Now, because I'm adding it onto this first vector, I'm not going to start at 0, 0. I'm going to start from the end of that vector. And this says my x is going to go in the negative direction 4 places. So 1, 2, 3, 4. And then my y is going to go down 3. 1, 2, 3. So that is what that addition vector looks like. So where the second vector ends tells me where that summation vector ends. That's the terminal point of this addition. So I could go ahead and draw this like this. Okay. So if I did this correctly, when I take my orange complex number and I add it to my pink complex number, I should end up with this blue vector. So let's double check. Let's double check just by combining like terms. If I do 6 and I combine it with -4, that gives me a 2. If I combine -2i and -3i, that gives me -5i, right? So that means on my x-axis, I should be going to 2, which notice my vector is at 2. And then on my y-axis, 1, 2, 3, 4, 5, I should be down at -5. So I can double check that I ended up with the correct answer. Okay. All right, so now that we kind of have this visualization of a vector created by a complex number, now we're going to go ahead and take a step back and relate it back to trigonometry, okay? So how is this related to trigonometry? Here's what we're going to do. We're going to take a random vector, okay? Random vector. Let me just draw one. Doesn't matter, we're not going to count the dots. Let's say this is our random vector, okay? And this is our terminal point where this vector ends, xy, okay? If I have any vector, I should be able to label this vector in regards to a reference triangle, right? So I could drop this down to make a triangle, and I could say that this is my y distance, or my y side length, right? This would be my x side length, and that this over here, my r, right, was my radius length or my hypotenuse length, right? And then we could define this whole reference triangle by this angle that we get starting from our x-axis as the initial side, right, and going up to that vector as our terminal side. So this is something we've done, right? This is how we defined all of our trig functions. So what we want to do is take what we have here and define our x and our y in regards to theta, okay? Because we're trying to switch from rectangular form, which is just an xy axis, into a trigonometry or polar coordinates, which incorporate our theta, okay? So we want to be able to write x and y in terms of our angle and our radius. So let's look at x, right? I want to see how x and r are related. Well, we know if we use x and r, and we're talking about this angle theta, the x is the adjacent side, and the r is the hypotenuse, right? And we have a trig function that relates adjacent and hypotenuse, right? Which is cosine. So we could say that cosine theta is equal to x over r, right? And if we're trying to define x, that's what we're trying to look for, how would I get x by itself in this equation? Well, right now, x is being divided by r. So to undo that division, I could multiply by r on both sides. So if I multiply this side by r, that would give me r cosine theta. And if I multiply this side by r, that r would cancel and I would just get x, right? So I can write x as r cosine theta. Okay? And what this does is it's basically relating that real number part, right? That real distance that we can count, which is x, that real number part x, to the magnitude and the direction of theta. Okay? So let me just write that. That way if you look back at this, you know what we're talking about. This relates the real part, which we're calling x, to the magnitude or direction of theta. Okay, so now we can express our x in terms of that radius or that vector length, right? And our theta, which tells us the direction, right? If it's a positive theta, we know we're going clockwise. If it's a negative theta, we're going sorry, I said that backwards. If it's a positive theta, right, we're going counterclockwise. If it's a negative theta, then we're going clockwise. Okay. All right. So just like we did that for x, we should also be able to do it for y. So if I want to use y and the vector that I came up with, whose distance here is r, right, or whose magnitude is r, then r and y can be expressed in a trig function because this is opposite my angle theta and my hypotenuse of my angle theta, right? So that's our sine function. So we could say, let me use a different color so it doesn't all start running together. So we could say that our sine theta is equal to y over r. And then just like we solved the cosine one for x, now we're going to we're going to solve this one for y. So we can do that by multiplying on both sides by r. So that's going to give me r sine theta is equal to, when I multiply by r on this side, my r's will cancel, and I'm just left with a y. So we can express our y value here as r sine theta. Okay, so what this one is relating is this y part. Okay, and remember the y part, that's our vertical change, right? And our y part is in regards to our imaginary part of the complex number. So what this one does is this relates the imaginary part, which we're calling y, to the magnitude or direction of theta. Okay, so this is not something that I'm going to have you prove or do whatever, but you are responsible for knowing how to write x and y in regards to your r and your theta. Okay, so here's how we're going to relate rectangular form to polar form. Rectangular form is what we're used to. This is just a complex number, right? So if we're given any a plus bi complex number, actually I should use a different color so that doesn't relate to what I wrote above. Okay, so if we're given some a plus bi, any complex number, we call that its rectangular form because that's how we can form our vector, right? Well, now we just determined that our x can be written as r cosine theta. So if I write r cosine theta instead of x, I would have r cosine theta. And then instead of y, if I write r sine theta, then I would have r sine theta times I, right? Because complex numbers have an I on their imaginary unit. So this is just rewriting it. Now, a lot of times in this textbook, they'll go ahead and factor the r out, and they will call this right here the polar form. Okay, Okay. Now, this and this mean the same thing. On an exam, I would be fine with you stopping here or stopping here if I ask you to write something in polar form. Okay. And then this is something I included just because you might see it in my math lab. I'm not sure. This is just shorthand notation. Anytime you see this CIS, this is just an abbreviation for cosine theta plus I sine theta. So they're taking the CIS and just writing it as cis theta. I will not be using this abbreviation, but I'm not sure if my math lab references that or not. So I wanted to make sure you had it in your notes. Okay. All right. So if we know X and Y, we should be able to write something in polar form, right? And the same way, we should be able to write R and theta if we know X and Y. So that's what I'm going to do down here below, okay? So we want to know what R is. Well, if I look back up here at my triangle, remember R is this distance, right? Or this magnitude of this vector. And normally the way that we find this distance, right, is we just use the Pythagorean theorem, right? If we know the X unit and we know the Y unit, then we can just square those, add them together, and take the square root to find R. So nothing changes. Same thing here, right? R is the square root of X squared plus Y squared, okay? If that's not explained enough, reach out to me. I'm happy to break that down further, but it's really just using the Pythagorean theorem to solve for R, which we've done a lot in this class, right? And then to find our theta, if we actually want to know what this angle is that we're talking about up here in our reference triangle, then we need to be given an X and a Y, right? If we're given an X and a Y, we can find theta. So I'm going to go ahead and say if we are given an X and Y, we can find theta, right? Because all we have to do is a ratio of X and Y, right? Relating it to find the actual angle, we need a trig function that relates X and Y. And the trig function that we have that relates X and Y, because if you look up here, X is our adjacent side, Y is our opposite. So adjacent over opposite is cotangent, right? Or we could do opposite over adjacent and do tangent. So I'm going to stick with tangent, and you'll see why here in a minute. So if I want to find the tangent of theta, I do Y over X, right? But remember, we're solving for theta, right? Not tangent theta. We're trying to figure out what theta is. So to get rid of this tangent, all I have to do is use its inverse trig function. So I would take, not cotangent. I don't know what I'm writing. I'm making up stuff. Inverse, not reciprocal. We're going to take the inverse function, which is our notation that says tangent to the little -1, right, of tangent theta is equal to tangent inverse of Y over X. So our tangent inverse and our tangent cancel, and we could write our theta as tangent inverse of Y over X. Okay, so now we have a shortcut method to figure out everything that we need to know, right? We know how to find our X if we know our, or let's say it this way, if we know what R and theta are, if I know R and I know theta, I should be able to find X, and I should also be able to find Y if I know R and theta, right? So that's going from polar form to rectangular form, right? If I happen to know what X and Y are, then I can figure out what R and theta is. So I should be able to go from this rectangular form to polar form by just knowing two things. If I'm given polar form, then I should be able to look at this and figure out what X and Y are. Or if I am given my x and my y, I should be able to figure out what my r and my theta angle is. Okay? All right, so let's look at applying that now. So on this first one, this one says we want to express 10 times cosine of 135 degrees plus I sine of 135 degrees in its rectangular form. So right now, this is polar form, right? This whole thing right here is its polar form. And just from the other side, I'm just going to write down what polar form was. Polar form was r, remember they factored it out, r times cosine theta plus I sine theta. That's its polar form. That's what it's currently in, right? And we want to take it back to rectangular form. Remember, rectangular form looks like x plus yi. Okay? So what they're giving us is they're giving us the r value, right? That's the 10 that's written out here. And they're giving us the angle. So if we know the r and the angle, we should be able to figure out what x and y are. Now, just for easy reference, I'm going to go ahead and write over here to the side those formulas we got from the last page. From last page. So we know that x is equal to r cosine theta. We know that y is equal to r sine theta. We know that we can find r by taking the square root of x squared plus y squared. And we know that we can find theta by taking the tangent inverse of y over x. Okay, so this is all what we learned on the last page. Okay, all right, so let's see what we want to apply here. Excuse me. I see that 10, because it's factored out of these two terms, that has to be our radius value. So we know that is r. And then I can already see that the angle is given, right? This is our theta, and it equals 135 degrees. So I know what my r value is, I know what my theta value is, and this is what I'm working towards, is to get it as x plus yi. So I need to figure out what x is, and I need to figure out what y is, and then I can write it together. So all I'm going to do is look at my little shortcut over here from the last page. X is equal to r cosine theta. So our r is 10 times the cosine of 135 degrees. And now I just need to simplify this, right? Now make sure when you're simplifying your trig function, they should give you nice, pretty, friendly angle functions here. 135, that's in quadrant 2, right? It's between 90 and 180. It's actually specifically perfectly between 90 and 180. So that's a 45-degree reference angle, right? And 135 is in quadrant 2, so its cosine is going to be negative, right? And if you remember, the cosine of a 45-degree angle is square root of 2 over 2. And because it's in quadrant 2, we know the cosine is negative, right? Excuse me. So when I simplify this, I can reduce the 10 and the 2. 2 goes into 10 5 times. So I end up with negative 5 root 2. So I now know my x value. Now I need to know my y value. So using my little shortcut here, y is equal to r sine theta. So I plug in my r and my theta. R is 10. Theta is 135 degrees. So I have 10 times the sine of 135. Now, 135 again is a 45-degree angle. So remember, sine and cosine are the same on 45-degree angles. But since we're dealing with sine in the second quadrant, it should be positive. So positive square root of 2 over 2. And then we just reduce this. So 2 goes into 10 5 times. So we end up with 5 square roots of 2. Okay, so we know what our x is and we know what our y is, so the last thing we need to do is just write it together, right? So rectangular form is x plus yi. So when we put in what we got for x and what we got for y, our x we found to be negative 5 square root of 2. And our y, so we're adding our y times I. This was our y, so 5 root 2i. So this is going to be my solution, or my rectangular form of this polar coordinate. Okay? Does that kind of make sense? Now, I know a lot of times some people like to write the I in front of the radical. If you wrote this as 5i square root of 2, that's totally fine with me. I'm writing the I at the end because I think that's how it does it in my math lab for this section. Since it's supposed to be written as x plus yi, they usually leave the I at the end. So make sure if you're typing in a solution that you make sure after you type this 2, you move your cursor out from under the square root before you type the I, okay? Okay, so this example was taking something in polar form and writing it back in rectangular form. I want you to also be able to go the other way. If I give you something in rectangular form, I want you to be able to write the polar form. So let's look at that direction now. So for these, it says we want to write it in polar or trigonometric form, and it's given to us in rectangular form. So right now, this is rectangular form, right? This is x plus yi, right? It's in rectangular form. So if I want it in polar form, I want to end up with r times cosine theta plus I sine theta. This is how I want my answer to be written, right? So if I want my answer to be written like this, I need to know two things, right? I need to know my R value and I need to know that theta value. And right now, I don't have either of those, right? All I have is my rectangular form. So this tells me that x is equal to 8, right? Because that's my real number part. And my y is the imaginary part, which is a negative 8. So if I know what x is and I know what y is, I should be able to find r, correct? If I look back up here. Because remember, r is just utilizing the Pythagorean theorem to figure out the magnitude or the distance of that vector, right? So I can find r. R is equal to the square root of x squared plus y squared. So if I plug in my numbers, r is equal to the square root of 8 squared plus negative 8 squared, right? So r is equal to the square root of 64 plus 64. So that means that r is equal to the square root of 128, right? And then we do want to simplify it. I do want to see if there is a way to simplify this radical. 128 is not a perfect square, but it might have a perfect square within it, right? We got 128 by doing 64 plus 64. So if I were to break this down, right, 128 is 64 times 2, right? And then 64 is 8 times 8. So since I have 2 copies, that tells me I can bring an 8 out, right? And I would still have a 2 left under the radical. So that means that my r is 8 that I brought out times the square root of 2, which I didn't have 2 copies of, so I had to leave it in there, right? Okay, so again, we're trying to write our rectangular form in polar form. So in order to do that, we needed to know r, which now we know what r is. The next thing is we need to know theta. So looking back up here at the top of my page, theta we can find by taking the tangent inverse of our ratio y over x. So theta is equal to taking tangent inverse of y over x. So my y is negative 8 over my x, which is positive 8. So we're doing tangent inverse of negative 1. And this is something that you can plug into your calculator. If you plug this into your calculator, you end up with negative 45 degrees. Okay. All right, so now that we know our angle and we know our r, now we should be able to write it in trigonometric or polar form. Okay, so here's my angle, here's my r, and all we have to do is rewrite this statement using those two bits of information. So my r is 8 square root of 2, and we write it factored out, right? And we do cosine of theta. So we're going to do cosine of negative 45 degrees plus I times the sine of our theta. So I sine negative 45 degrees. And that is our answer. That's how we leave it in polar coordinates. Okay. I want to show you one more like that, and then that will be the end of the section. Okay. The last one I want to show you is doing the same thing. It's taking it from rectangular form into polar form, but this one looks a little bit different, right? Because the difference between B and A is, notice here I only have a real number part. I don't have the imaginary term here, right? So if I was going to write this as x plus yi, I'm missing the yi term, right? So I could write this as negative 15 plus 0i, right? So if I wanted to try it, let's just try it for a second. If I wanted to visualize this, okay? If I wanted to visualize this, and I'm using the x-axis for my real numbers, and I'm using the y-axis for my imaginary numbers, and I wanted to graph this, my real number is out at negative 15. So I would go way out here to wherever negative 15 is, right? And then on my y-axis, I'm not going up or down, right? There's no imaginary part. So that means this is where my vector would be. I'd start at 0, 0, and it would just go out to negative 15 on my real number axis. Does that make sense? Excuse me. So just from that, just from looking at that one line, because there's no imaginary part, I should be able to easily figure out what my radius value is and what my theta value is. So remember, radius is the magnitude, right? Or the distance. So if I go from 0 out to negative 15, then my radius length, or that distance, is 15, right? Again, you could use this shortcut here, or not shortcut, but this formula, r equals the square root of x squared plus y squared. Your y would just be 0, right? And then you would square your negative 15 and then take the square root of it, which would leave you with a positive 15. So it is possible to do that. I just want to show you how you can think through it on these special cases. Okay, so we know our radius is 15. Then we need to know our theta. Well, you can look at this, if you just looked at this like it was a unit circle, right? The theta is how far we traveled. So in this case, it's straight out on the negative x-axis, which means our theta is 180 degrees. So now that we know our radius and we know our theta, now we can go ahead and write our polar form, which is r times cosine theta plus I sine theta. So we're just going to plug in our values. So our radius is 15, and then we would write cosine of 180 degrees plus I times the sine of 180 degrees. Okay, and we just leave it like that. Okay. All right, so that is the end of section 8.2. You should now be able to complete that assignment in my math lab. If you have any questions, please let me know.